Now it says REC.
Okay.
All right. Record. Okay.
All right. Okay, so, good morning. I'm going to talk about this in just a moment, but I thought it was a pretty thing to look at as we get started. Just an aside, that's an interesting one. Anyone know what it is?
It's an image.
It's the black body radiation of the universe, also known as the cosmic background radiation.
All right, I think that deserves a round of applause. That's exactly what it is. We're going to talk in our aside about that a little bit, but to begin with, we need to go back and just talk about generic black body radiation. All right, so as we closed out, I need to just make sure our announcement stuff. So apologies, I didn't have office hours yesterday. It was a little bit of an update. I'm hoping I'll have some time tomorrow afternoon. The way today is panning out, it probably won't happen, but I'm hoping I can have some time tomorrow afternoon. So stay tuned for that for office hour. Okay, so back to our exploration, rather superficial one, of radiation. And in particular, characteristics of this so-called black body radiation. And we talked on Tuesday about what this implies. It's the characteristic spectral distribution of the electromagnetic waves. So it's the EM spectrum associated with an object in thermal equilibrium with its environment. I'm not going to go into too much detail on this because we will possibly come back and talk a little bit about it towards the end of the semester in the context of electromagnetism. And as I closed out on Tuesday, I opened up possibly slightly intimidating looking expression for how this, let's say, energy density of electromagnetic radiation in a black body can be characterized. The details here for now are not really important, but I thought it was worth describing it. There it is, okay? So, just a reminder of what this is. Again, not so important right now. One thing that we can derive from this is a little bit more important. Okay, so what is it? It's the really the frequency spectrum, where this is an amount of, let's say, radiation, amount of energy at a particular frequency, or a black body radiator that has a temperature T. Okay, so a function of two variables for any particular temperature. This is obviously fixed, and then what we expect out of this is a frequency distribution. What does it look like? A few constants, some of which you know, some of which not yet. I'll come back to that in just a moment. The important frequency dependence sits over here, and you see that according to this prescription, it goes as f to the power third. So in that sense, diverging at high frequency, but it has a modifying factor in the denominator, which is e to the power h times f, where again f is the frequency, over k, Boltzmann constant, times temperature. Okay, so it's a bit complicated. I'll show you what this looks like in just a moment. Before doing so, let me come back to the h constant, which for most of you is not something, you've probably seen it before, but maybe not in any great detail. This is so-called Planck's constant. And I'm basically not going to say much about it, other than it is the constant in the physical world that sort of sets the scale when physics transitions from a classical description, which is what mostly you're doing in intro physics, to a more direct quantum description of phenomena. And So Planck's constant sort of characterizes the scale where quantum mechanics takes over from classical mechanics, okay? That's all we need to know about it for now. And I'm not even going to write up what its value is, because by and large we're not going to use it this semester. But it's kind of interesting that it has something to do, apparently, with quantum mechanics, and that's all I want to say about it. So, this is the standard black body radiation spectrum, as I mentioned, for a given temperature. It's obviously a function of the frequency. So let me just show you a couple of examples of that. Okay. Apologize, there's a lot of walking back and forwards in today's class. So, let's see if we can get this back. Projector on. Alright, so I just quickly into a search engine with black body spectrum. I want to find one that is explicitly as a function of frequency. Let's see what happens when I visit this. Is it going to be big or small? It's going to be small. Yeah. Alright, thank you. Let's try this. It doesn't really help, but okay. Not great. So what you're seeing here is good enough, okay? So there are four, it looks like, different color bands on this, and if you look at the legend for the image, those different colors correspond to different temperatures in Kelvin. And so along the horizontal axis is frequency in slightly hard to pass units, but it's in cycles per second or hertz. And then you can see here some rather large exponents in the frequency there, fine, okay. And then what you see on the vertical axis is some sort of measure of power or intensity. So what this is showing you is a sort of energy density spectrum for particular temperatures, and so obviously spans a range of frequencies. And then you'll see there's some fairly sharp turnover on the right-hand side. So the expression here with just the f to the cube power obviously has this diverging at high frequency, but when this kicks in, and it's a rather complicated dependence here with these factors, it essentially gives us a turnover on the right-hand side, and that's what we're seeing with the cutoff on the right-hand side here. All right, so these are characteristic black body radiation spectra, and we're going to talk briefly about the universe and its relevance to this, but another pretty good black body radiator is the sun. Now, if I tell you that the sun is a pretty good black body radiator and therefore follows this prescription in terms of its radiation spectrum, when you look at the sun, what, hopefully you don't have to do this directly, but what is the dominant color we associate with the sun? Yellow, right? So what that is telling us is a reflection of this, essentially, that this black body radiation spectrum peaks in the frequency or wavelength part of the spectrum associated with yellow light. Okay? And so you can see the peaks where they fall here for different temperatures, and you can fairly easily then sort of deduce, based on this, what the surface temperature of the sun is. And I asked you last week in a sort of general knowledge quiz at the end of one of the classes what that number is, and you might remember we said it's about 6,000 Kelvin. Okay? So the sun, pretty good black body radiator, peaks in the emission spectrum around the yellow part of the spectrum, and corresponding to about 6,000 Kelvin on a distribution that looks like this. Yeah.
In recitation, we were told that it peaks at green because it's something to do with like plants.
Well, what does the evidence tell you?
They're green.
Huh?
Plants are green.
Plants are green, but when you look at the sun, do you see it green?
Well,
I don't know, maybe you do. Okay, it's true, there's an interesting correlation there. To be honest, I don't quite remember the details, but it's true. I mean, yellow and green are fairly close on the spectrum.
I mean, I was just reporting what I was told, so.
Okay. What I want you to learn from intro physics is not just thermodynamics and electromagnetism, but a little skepticism. Okay. So if somebody tells you something, maybe it's right, maybe it's wrong, try and piece the pieces together. Anyway, yellow and green not so far away on the spectrum. And yes, there is apparently some correlation between the evolutionary progression of plant life on the planet and the spectrum of the sun. All right, anyway, this is what it looks like here on a frequency spectrum. Of course, though we haven't formally covered this ourselves yet. We can also plot it on a wavelength spectrum. Oh, I just lost the page of images, so let's see if I can get it back. So I can also plot it on the wavelength spectrum. Maybe I'll choose this one. Interesting. Maybe not quite what I was expecting. Maybe those colors are not, I think they're not supposed to represent anything actual. Anyway, this is just inverting things by making use of an expression that we will use quite a lot at the end of the semester, which is to say that the frequency and wavelength of electromagnetic radiation in light can be related by a simple expression like this. So where this is written in terms of frequency, I could in principle express it in terms of wavelength, and that's what you're seeing on a distribution that looks like this. Okay. All right. So those are the general characteristics of the blackbody emission spectrum. One thing that is going to be most useful for us when we talk about thermal energy transfer is not the details of the spectral behavior, but the total amount of energy that's transmitted through a radiated process. So let me just quickly say something about that, so I can recover my chalk. And I'll tell you what this looks like when we integrate the entire spectrum. Okay, so this is the spectral behavior. For us, we're mostly interested in the total energy transfer. So the integrated energy or power. It's not a trivial thing to integrate. But if I do, it turns out that I get an expression that looks like this. We just write it up and we'll talk about it. All right, and this is the thing we're actually going to use more often than not in calculations in this part of the course. So what is it? This is the radiated power per unit area. And again, not a trivial thing to integrate by any means, but when you do, you get a rather simple result out of it. And it tells us that the radiated power has a very strong dependence on the temperature of this object. It in fact goes as the fourth power of the temperature, the absolute temperature. So this is pretty dramatic. And of course there's a constant in here, happens to be called the Stefan-Boltzmann constant. And this time I am going to write down what it is, because it's something we're actually going to do some calculations with, albeit not many. And it has a value which is around 6 times 10 to the minus 8. That's supposed to be a 5.7. 6 times 10 to the minus 8 watts per meter squared per Kelvin to the power 4. Okay, obviously dimensionally consistent. So this turns out to be the one thing that you're actually going to use in the near term from this radiation sort of investigation. And this is going to tell us now something about how we can calculate really, in our setting, thermal energy transfer via radiation. That's pretty much all I want you to know about this. Any quick questions on that? All right, so I mentioned I wanted to do a quick aside. I do, just because it's so much of current interest. And that's to talk about the blackbody radiation in the setting of the universe as a whole. I'll try and be brief on this. Back in the 60s. Not too far away from here, in New Jersey, at the site of what in those days was Bell Labs, a very famous place for fundamental research in physical sciences. Back in the day there, a couple of scientists had built and were commissioning a large, essentially, antenna or transmitter or receiver for radiation in the microwave part of the spectrum. Okay, so microwaves, and again, we're going to talk more about this towards the end of the semester, are part of the electromagnetic spectrum. You know about microwaves most commonly in the context of something you might have in your kitchen. So it's a part of the electromagnetic spectrum which has wavelengths that are characteristically longer than the wavelengths of visible light. So these guys at Bell Labs back in the day have built this antenna, and we're actually, my understanding is, trying to use it to detect microwaves that were being emitted in Europe, actually, I believe in France, and trying to sort of see if they could detect microwaves that they anticipated were traveling across the Atlantic, and they'd be able to pick them up and start to better understand how to use that technology maybe for transmission of information. Anyway, as they were commissioning their apparatus, fairly soon after it was turned on, they found a kind of pervasive background, not just when their antenna was pointed towards France, but if they pointed it in any direction, at least any direction upwards towards the sky, they found this pervasive background that was unexpected. There's famously a few sort of anecdotes about all of this. The most amusing one is one of the first culprits that they thought was the reason for this. This was an antenna which was outside in the field somewhere. When they went to look at it to see what the source of the problem might be, they found a bunch of apparently pigeons nesting in it. And the thought was that somehow pigeons crapping in the antenna had caused this background signal in the microwave detector. Anyway, once they cleared all of that out, the signal was still there. And it turns out this was the first direct discovery of blackbody radiation from our universe as a whole. So there's a long and very important story behind this. But it turns out that if what at that time was still a rather sort of developing idea, I would say, if the theory, postulate that our universe was created in the Big Bang, hot, dense, subsequently expanded, you can work that model and it will essentially predict at a certain point that the universe was roughly in thermal equilibrium. Early on, it was hot and dense enough that constituent components like atoms were not electrically neutral, and they were in fact ionized. And so the very early universe had this sort of ionized plasma of stuff in it, but as the universe expanded and cooled, of course it did cool, and eventually it was cool enough that those nuclei and electrons could associate and become neutral atoms. If that happens, and again this was very much at the time when the Big Bang theory of the universe was still very much under development, if that happens at the point where the constituent atoms become electrically neutral again, the expectation is that the universe suddenly goes from being opaque to light travel to being transparent. And if all of this is true, at that point, which happens to be about 400,000 years after the start of our universe, the whole universe should be filled with a kind of uniform bath of electromagnetic radiation corresponding with a black body radiator. Now, interestingly, this is what these guys discovered in their antenna in New Jersey. Of course, the universe since 13.3 billion years ago has expanded a lot. And something else we'll try and cover at the end of the semester. As the universe has expanded, electromagnetic waves within it have been stretched, essentially by a sort of redshift phenomenon. And so that early black-body radiation emitted after 400,000 years of our universe's existence, which was originally corresponding to a black-body temperature that was quite hot, now corresponds, because of the wavelength stretching and the redshifting to a temperature of about 2.7 Kelvin, okay? So I'm just going to write, this is all general information, by the way. So this is now the so-called cosmic microwave background radiation, or CMB. And it corresponds to a black body spectrum of a temperature of about 2.7 Kelvin, okay? Very cold, obviously. That's what these guys detected. And it's turned out to be incredibly important in the development of cosmology, primarily, over the subsequent half century. And the image that I showed you, and I'm going to show you again, is actually now a sort of more contemporary image of that radiation. So I'm going to try and wrap this up pretty quick because we need to get back to important stuff. But this has become a very sort of iconic image over the past 20 years or so. This is an image of the entire sky in Milky Way galactic coordinates. So the Milky Way galaxy, of which of course we're part, sort of spans the long axis of this ellipse, and then as you look up and down, you're looking away from the plane of the Milky Way galaxy. What this image shows is obviously computer colored. What it shows is, in fact, that while if I look almost anywhere in space, I see a black body radiation spectrum that corresponds to a temperature of about 2.7 Kelvin. That's true. It's very uniform, but it's not completely uniform. It turns out if you look in different parts of the sky, the temperature, if you measure this very carefully, which it corresponds to, varies by about 1 part in 100,000. Okay, now, does that sound like a big deal? Maybe not. This color-enhanced image, or color-represented image, shows the variations at the level of about 1 part in 100,000 in the temperature associated with the black body radiation of our universe. So it's very uniform, but not perfectly so. And these deviations from uniformity turn out to carry a huge amount of information about how our universe got to be the way it is. So if you analyze this carefully, you can learn a lot about not just the radiation, but you can learn a lot about the makeup of our universe. You can learn a lot about the early phases of our universe and what was going on in those early few 100,000 years. But even more dramatically, you can learn about what happened within just the first few seconds by measuring this distribution really carefully. So, cosmic microwave background radiation, nice example of a black body radiation spectrum. And again, for those of you who are interested, this has become a source of a huge amount of progress in cosmology in recent decades. So I just wanted to mention it since we're talking about this. It seems nice to kind of touch base with some contemporary research in physics and cosmology whenever possible. So I'm going to stop there, and then we're going to turn back our attention to sort of more on the syllabus material. But any questions about this stuff? All right. So, something to know about general knowledge and black body radiation. Okay, so let's come back to ideal gases. We'll talk a little bit about slightly less ideal gases, and then we're going to turn our attention to the microscopic approach to understanding all of this. So, remember the basic idea underpinning our ideal gas behavior is that we have non-interacting constituents. Well, what does this really mean? Non-interacting essentially means they are constituents, atoms, molecules, they're bouncing around inside the volume of gas. And the only interactions they have are elastic collisions with each other. Okay? So that's the sense in which I mean non-interacting. So last semester, a good amount about elastic collisions. We're going to talk about that in a little while when we try and probe this at the microscopic level. Now, of course, that's an idealization, and in reality, not terribly likely to be true. We talked about this already. So usually this means it's a dilute gas. The constituent atoms, molecules, on average, are not so close to each other. And in fact, we also kind of implicitly assume that the constituents themselves, atoms or molecules, are kind of point-like. And that's sort of tied in with this approximation or assumption that it's a dilute gas. It's basically saying that the constituents don't take up any appreciable amount of the volume. Okay? So those are sort of two things that go into our ideal gas model or assumptions. And what we know now is the kind of governing relationship in terms of macroscopic behaviors is most simply expressed by something that looks like this, the ideal gas equation. And this, of course, is counting on a molar basis. As we saw last week, we can also count on a number of molecules, number of atoms basis, in which case this becomes a capital N and this becomes Boltzmann's constant. Okay, but for now we're going to stick with things on a molar basis. All right, so how valid is this? Well, not great. It is okay for dilute gases, and in terms of the non-interacting aspect of this, you could imagine that certain types of constituent atoms might better satisfy this requirement than others. Just your awakeness and your general knowledge, if I was to ask you which type of gases might best satisfy this behavior, what would you tell me? Yeah, noble gases. I'm sure all of you know this. What's special about the noble gases that makes them more likely than anything else to satisfy this criterion? Yeah, let's go with that. They're inert, chemically inert, right? They have atomic shell structures that mean they don't particularly like to combine with anything else. So noble gases are pretty good, and of course dilute noble gases are about as good as we can get. Even better, dilute gases that have small constituent molecules. So helium would be about the best possible example we can get towards this ideal gas behavior. All right, so that's some of the stuff underpinning ideal gas. What about less ideal gases? And this is a little bit of an empirical change. And so what we can sort of parameterize is a modification to the ideal gas equation that takes account of essentially non-zero intermolecular forces, and it also takes some account of maybe the finite size of the gas constituents compared to the volume in which, the free volume in which they find themselves. Quick aside on this, and then I'll just write up the sort of modified equation. What can you tell me generically about the behavior between two identical atoms if you vary the distance between them, so the distance between their centers? Knowing whatever you know so far about how atoms are made up, maybe other pieces of information, how might you characterize the general force versus separation between two identical atoms?
As you increase the distance, it's the force between them decreases, and then I think after some point it comes back.
Just if you can just say it a little louder.
As you increase separation between the two, it first goes from like infinity to like its minimum, and then again comes back up and increases more slowly.
Okay. Anyone else, I mean, I think what you said is fine, I just want to see if anyone else wants to say anything additional or differently. Yeah,
I guess to go off what you said, like you reach, it starts like at like a